It's a pleasure to be here tonight with my colleagues Josh and Khyati, and thanks for having us at ACM. So we're going to talk about some innovative applications. We built learning, deep learning, the three of us. What I'm going to do first is go through a bit of an overview about deep learning, debunk some myths, and then I'm going to go through a project, a crypto project, and then pass it over to my colleagues, and then we'll do a Q&A, panel Q&A at the end. So I saw this stat when I was reading that said that less than 1% of production machine learning projects use deep learning. So I'm curious, let's get our own data. So how many people have done a project with deep learning? Raise your hand. All right. And how many people have deployed a project with deep learning in production? Raise your hand. Okay. How many people have...
Back to the audience.
Oh,
How many are seen?
So I saw 2-ish on the deployed in, 3-ish deployed in production. The ish was a ish. How many of people have deployed more than 5 projects in production with deep learning? 5. Okay, 5. We have 1. All right. And how many people do we have? 100? Okay, so that's 1, 2, 3, 4%, right? So not far off. So I'm Michelle Bonat. My goal is to get more people using deep learning in production, and the reason I want that to happen is because deep learning speeds innovation. If we could speed innovation, we can make the world a better place. So we're here to take you through that and get it accelerated. So what is deep learning? So when I started thinking about this, it sounded complicated, it sounded like a dark art, it sounded like you needed a wand. It's actually not. So if you take anything away from this, what I'd like you to take away is what it says right here. Deep learning is just a large, deep neural net. So a neural net, we all know what that is. Think of one with a lot of layers. So on top you see a typical machine learning project. Takes data on one side, transforms it using a model, and learns, brings it to the other side. In the middle, it's a more complicated version of that. And at the bottom is deep learning. All it is layers in between. Sometimes you hear them called hidden layers because you can't see them from the top. And again, it goes from the left to the right with a series of learnings, models, data in that. Data can be everything from raw to processed to human, labeled. And you'll hear models like ANN or CNN, RNN, LSTM. So what do you take away? Just a large, deep neural net. Just a bunch of layers. You got this, right? So when people say how many layers, Dr. Eva will say 1,000,000 layers. You can actually get by with much less than 1,000,000 layers. So in my learning about deep learning, I've overcome some preconceptions, and I wanted to go through some of those. So true, false, maybe. Let's all do this together. So deep learning is too confusing, so we should confine it to a lab. Wow, false. We're here to help jumpstart that. Deep learning is only useful if you have a lot of data. True, maybe. Well, I submit false. Experts have said you need 100,000 data points to get started with deep learning. You can effectively get started with less than that, but for sure, deep learning scales better on a lot of data. And you see that in the graph here. So So the third one, deep learning won't work unless you have super powerful hardware to run it on. Okay. All right, friends don't let friends run deep learning on hardware, right? So we have AWS, we have Google, and did you all see that Colab, which is from Google, recently made available a free GPU? So free as in zero money. Deep learning takes a lot of code. True? No. Right? Okay, so here's deep learning in 7 lines of code. This is from a chatbot. And you can see what they're doing here. They're building the neural network. They input their data, run through that, and then they instantiate the DNN, the deep neural network. So some of it is abstracted, but that's 7 lines of code. In the project I'm going to show you, my deep learning section is essentially 1 page of code. Deep learning should be tried first for complex problems. What do you think? So let me say this a bit more clearly. Should you always try deep learning first if you have a complex problem? Well, you should always start with the skateboard version. You should put your bulldog on a skateboard the quickest way you can and get that bulldog down the sidewalk. Get him going. And then add in deep learning when you know what your project needs and you understand the data. Deep learning is hard to train, almost an art form, a dark art. There are some areas. Yeah, so I put that as a maybe. So this is why, we're professionals in Silicon Valley doing this great stuff. But you can do things. You can research and learn what the best approach may be. You can start with a smaller learning rate and iterate. That way you can play with dropout. You can cancel some neurons. You can leave the first layers untouched. This is an example of some dropout, and you could see that they're just going through that line by line. Right, so there are tools and ways to approach that, and then deep learning has poor interpretability. I see a lot of head nods. I happen to agree with that. Has anyone tried Lime? So Lime is a package, so you just do a pip install to get it, and it's helps you explain the predictions of your machine learning model. I haven't tried it, I've heard it recommended. But I've also heard people say that they haven't used deep learning in corporate projects because they do need it to be very interpretable. So hopefully this will help drive that visibility. Okay, so now some of the myths are debunked at least, and we're going to go through the examples. So I'm going to go through a project I did in financial services using crypto and blockchain. Josh is going to give you a vision of healthcare through the ICR, and Khyati is going to do computer vision. So if you'd like to get a copy of these slides, you can hit my personal website, which is michellebonat.com. Yes?
Would you mind posting them in a link to the meetup site? There's like a discussion thread, and then you can just post the link there.
Of course I will, yes. Ethereum flow predictor gazing into the crypto ball. So what we're going to show you are each of the personal projects we did at a program called Insight Data Science, where we were AI engineering fellows this past fall. We finished at the end of the year. And Insight is a 2-month, very intensive program where you collaborate with colleagues, you build real-world applications, and you also learn from each other. And each person does a personal project. They're 4 weeks in duration. So literally 4 weeks from I'm starting to think about it, I've chosen one from the list, to I've done my presentation and my front end, 4 weeks. So part of the reason we wanted to come today is to show you, you can do deep learning in 4 weeks and get something going. So I chose this. This was a consulting project for a local venture capital firm. And I was really intrigued because cryptocurrency has grown really quickly. It's more than 200 billion asset value. All the flows are publicly recorded. All the information is mostly recorded because it's blockchain, other than who actually is the final owner. And I was further intrigued because I started my career as a financial quant modeling traditional financial markets. So I was really interested in this new sort of crypto market. And then this can be applied, certainly extended into really any kind of binary classification model. Anything that needs a binary classification model, like predicting account cash flows or even predicting customer churn. Okay, so the problem to be solved is given an Ethereum address. Ethereum is a type of cryptocurrency. Think of Bitcoin 2.0. To do two things: predict if the funds will be transferred out, so if the funds will move, and what are the signals driving that. And the larger motivation, certainly is anytime you can predict the funds flowing in a financial market, that's really the keys to the kingdom. So I'll quickly explain how blockchain works. So someone requests a transaction. The transaction is broadcast across the network. Miners verify that it's correct. Then those transactions are combined to perform a data block. That new block is added to the blockchain, and the transaction is complete. That's all you need to know. Blockchain is all that, and it's really pretty simple. So here's my data pipeline for this project. I took the I found the Ethereum transactions data, which is in GCP, Google Cloud. It's about a terabyte of data, about 15 million transactions per month. I wrote some custom SQL queries looking at that data, created some custom data sets, which I then munged and analyzed through several rounds to understand, working with my subject matter experts, what was important and what I could maybe ignore. Did a few rounds of that, and then I actually ended up pulling the specific account transaction history for the relevant accounts all the way back to the beginning of the year, January 1. And then I built a flow predictor. I did that using 3 different machine learning models, including deep learning. And my deliverable was the flow predictor signals. Okay? It's kind of a mouthful, but I'll show you step by step. This is some of what the first pass was, and I did this without any kind of machine learning or deep learning. I did some data analysis, some graphs, some histograms, worked with my SMEs, and what I learned was that there are a lot of microtransactions, pennies, pennies, pennies. Those aren't interesting. There's a lot of exchanges, they call it, that are high volume of transactions that are really, noise on the other side. And there's other terms that prove to be uninformative, like gas. And so what I did is I crafted some data sets that I took some of that out. And you can see what's circled here is a proxy for eliminating the exchange accounts, the high transaction accounts. And then these are some of the features that I worked with. You can see it was what time the transaction happened, what's the value, what is the price in the market before. And then based on my analysis, I knew I could take some things out, like how much they paid. So I did a series of 3 experiments, 3 different machine learning models. My first was getting that bulldog on a skateboard, logistic regression, of course. My second experiment was random forest, so chose an ensemble method to get a portfolio combination of learners, and I used random forest to, chose a bagging method to reduce the variance because I was worried about noisy data. And then I added, brought in the heavy artillery with deep learning. So what happened? Random forest actually won with the current iteration given the current time. So here are the metrics. I'll go through the metrics quickly and then I'll explain a little bit what it is. So the accuracy you could see was very high across the board, right? But you would expect that because this is looking at a data set to see if the account moved money, effectively if they sold on a certain day. And you would expect that most of them did not move money, did not sell. So a human could say 100% of the time, I'm going to say no, or a little bit less, and you'd be pretty accurate. So we really discounted this accuracy metric and dug in further. And then what you can see is that random forest outperformed both the logistic regression and the deep learning. But let me tell you a little bit of the backstory. So random forest, I did pretty light trees. I did use grid search, CV grid search cross-validation. And so I was able to tune my hyperparameters that way, which gave me some boost, or it gave me some benefit. And then on the deep learning, I did massage it a bit. So I did fairly small batch sizes, 2,000 epochs, and I did 4 hidden layers. And as I ramped it up, I could tell that it was overfitting. It was starting to overfit. So random forest is the current winner. Left the cat out of the bag. So what do you think was the biggest driver? The biggest driver was actually the value out to predict whether they would move the money. Value out, and second place was the historical price in the market and actually the transaction fee. And surprisingly, you can see on the bottom, the time of the transaction was 0 impact. So my hypothesis going in is I thought maybe people dump it on a Friday to get money to go out. Turns out Ethereum is such a global market that it's happening around the clock in so many time zones. The time of transaction was literally, not predictive at all. Yeah. So I'll touch on some challenges and learnings and some next steps, and then I'll queue up Josh. So challenges and learnings, anything in crypto, you might hear it's a lot of data munging. It was for sure. There were no, pre-chewed data sets that would work for me, so I created my own. I did find some data discrepancies, so I encourage anyone for any type of machine learning or data science to QA your data really early. So for example, I found one of the APIs was incorrect and I had to manually pull that data. Fun. And then keep an open mind, because features that you might think are the drivers, like I thought the time of day, the time of the day of the week, were complete non-factors, and I had left my model open to discover that, so I encourage you to do that as well. And so next step, so a little bit more about deep learning. So deep learning didn't win. Something to think about here is it's a very imbalanced data set, so doing some subsampling or even perhaps rescoping the project and saying, instead of just one day of transferring the funds over a month and do a longer period of time, more data, would be, the next step in that project. So what I really want to impress upon you is, to do all of this in 4 weeks is very achievable. And we did get a strong signal. So that's going to wrap up my portion. I'm Michelle Bonat. You can see some of my background, ways to contact me. And this is a picture of my rescue pup, Malia, who is part Labrador Retriever and part kangaroo. So I'm turning it over to Dr. D.
Sorry, I quickly need to get this and this one, right?
So I really want to thank everybody for coming today. I want to thank Walmart Labs for, huh?
You want me to just flip your slides?
Oh no, I'm good. I'm good.
Right here.
Thank you so much. Yeah, I want to thank Walmart Labs for supporting this event and food, as well as ACM for hosting, and all of you for coming out today. So I kind of geared my talk to talk about some fundamentals of machine learning and data science, and I do touch a little bit on deep learning here. But I want to know in the audience today, how many beginners or novices are in the audience today? Don't be afraid. Okay, so that's a little bit less than, a little bit more than 1%, right? Yeah. And really what I want to do is give you an idea for the foundations of these kind of things and some intuition about what kind of projects can you apply data science or deep learning to. Again, this is a project that we worked on at Insight, and it's a 4-week sort of basher to try and create a minimally viable product during that time. My project is I'm trying to identify at-risk patients using intensive care unit data. Okay. Oop. So what are some reasons that we might want to monitor mortality risk? And there are a lot of ethical questions here, but putting those aside for now. Some of the benefits are we'll be able to select medications for patients that have a greater chance of success. We might be able to suggest if a surgical procedure is too risky to be performed on a certain patient. Another thing is that we might be able to intervene on time for patients who need the attention of doctors the most. So what's the problem here? The problem is that the ICUs have all of this data. There's over 7,000 pieces of information that are logged into electronic medical records every day. But these software that these hospitals are using, they're not equipped to do any analytics or analysis. So the result of that is that your doctors are unable to use all of the data that's at their disposal. In fact, some studies estimate that doctors, in terms of predicting a patient's mortality, they have up to a 58% false negative rate. What does a false negative mean in this context? That means that this doctor predicts that this patient is not going to die, and they do during their ICU stay. So that's what a false negative is in this context. And obviously, we really want to minimize that as much as possible. Can everybody hear me well? Yeah? Okay. Thanks. What's the solution? Well, I decided to name my product Vulcan. And a lot of people didn't understand why we called it Vulcan because it was a lot of younger people. But you and I both know, live long and prosper, right? Everybody gets that. So I got the right audience. And this would supplement existing electronic medical records. And the idea here is that you would have a dashboard on which each patient would display their mortality risk as well as risk factors for that patient, whether they had high or low sodium, their blood pressure, their temperature, and these kind of features. What are features? Features are basically aspects of your data that you're using to make predictions. That's what, when data scientists or deep learning aficionados are talking about features, that's what they're talking about, is that this is some kind of thing that we're using to predict some outcome. And the success metric for this project is high sensitivity, which is, like I said, we really want to minimize that false negative rate because false negatives cost a lot of resources. Families who we may believe that a certain patient is not going to die, and then if it's too late to intervene, then hospitals are going to use every resource at their disposal to help these patients, right? So we want to optimize the distribution of these resources. So how do we tackle this problem? Often the key to solving the problem is formulating and sort of translating the problem from whatever your boss is telling you or the executives are telling you, and translating that into a machine learning or a data science problem, okay? So the goal here is we want to predict the probability that a patient will die in the hospital. And it turns out that for many models that are used in statistics, they already predict this. They use a model that takes in the features and gives you a probability of a certain outcome for a certain class, okay? So using these models, you can calculate the probability that a certain example, so in this case, an example would be a patient, and the set of features that belong to that patient during their stay in the ICU, and we can predict the probability that that patient belongs to a certain class. So of course, in order to train a model, you need data, right? So I use this data set that's called the Mimic3 data set. It's maintained by MIT. It has 40,000 patients, and that includes their lab tests, such as their red blood cell count, white blood cell count, just a blood test or any other test that a lab would perform, as well as sensor data. So that includes like a heart rate monitor, a blood pressure monitor, and things like that, as well as the diagnoses by the doctor. So at first glance, do you guys think that this is a really sanitized data set, or do you think this is a really messy data set? Yeah, I mean, it can. Yeah, that stuff is in there too. This is actually a very messy data set. And the reason why is, do you think you can put these data easily into an Excel spreadsheet? Right, it's going to be pretty difficult to do that, to get the data sort of in a tabular format, right? Also, there are a lot of features in this data set. In principle, there are millions of features here. I mean, I can do anything I want to with this. I could say the number of blood tests in the last hour, the number of doctor visits in the last. I could create any feature I want to, right? But how do you know which of those features are the most important to solve this problem? And we end up into a problem where if we have 40,000 training examples and there are 1,000 features, then there actually isn't that much data to solve this problem, right? Because if you cut it like, okay, say if you want to describe one dimension, you might need 10 training examples. For 2 dimensions, maybe you need 100. 3 dimensions, now you need 1,000, right? So if you have 1,000 dimensions in your problem, like that's really not a lot of data to solve this problem. So a lot of this data is missing in principle because not every patient has the same tests while they're in the ICU, as well as a lot of it's a time series, and it's an intermittent time series, which means that somebody's heart rate is taken every minute, but then for lab tests, maybe you get your lab tests only once every day or something like that, right? So we want to take this data set, which is just a SQL database, and perform some feature engineering, which means to take this messy data and to put it into an Excel table, right? So kind of like a tabular style of data. And then we're going to use this data in a classification algorithm, which is basically going to take these rows in the Excel table and give us a 1 or a 0, right? So it's going to determine the class of those examples. And then those are going to be served on kind of a dashboard. So I'm going to talk a little bit about feature engineering first. So you need to convert this raw data into tabular style features. And that way you can train your classification model. And it's really valuable here to have domain expertise, right? Because in principle, you don't know what's important. If you're just a statistician or a dumb computer scientist, oh, sorry. It's really helpful to have some domain expertise to help guide this process of engineering some of these features. So the problem I mentioned before is that some of the patient data is recorded every minute, whereas some is daily. So one way we could tackle this problem is to use a sliding window, a sliding 48-hour window. Every hour, that window moves, and within that window, we can extract some features. We can determine the average blood pressure of a patient within that window, the standard deviation or the variations within that feature within this window, or the minimum and the maximum values. Also, not every patient takes all of the lab tests or has all the sensors. Some of them are missing the data because not every patient has the same conditions, the same diagnoses, right? So how I chose to deal with this problem was to discard the features for which more than 80% of the data is missing. Now, I only had 4 weeks to do this project, so that was my decision. But actually, for your applications, that might not be a good decision, because even if a feature is missing 80% of its data, it still might be useful. Well, it's raining today, okay, but does it rain every day? That's why you have a data scientist here. Okay. So in principle, even if a feature is missing over 80% of its data, it still might be useful to know that, right? Because it might be something that's significant. But basically, how I chose to fill in any remaining data is to take whatever the last known values were for that patient. Or in the worst case, you could take an average value among all of the patients just to fill in the value. So different models vary in their ability to capture the complexity of the data set as well as their interpretability. And this is the question you have to ask yourself when you're doing these projects. What is the level of interpretability that is required by this project? Okay, do you just want something that's going to be accurate? Do you want a model that's going to be really fast? Do you want something that's going to be interpretable? And often the answer is that you should just use the simplest model that you can to solve the problem that you are trying to achieve. So that means choosing an interpretable model. One of the most interpretable classification models is logistic regression. Because literally all this is on the left-hand side, you could see this orange curve is a logistic model. All this is a sigmoid function with a linear model embedded inside of it. So you have actual coefficients that are physically interpretable. And you can ask yourself, do these coefficients align with my intuition about this problem? Do I believe that as the number of rooms in a house increases, that the price of the house will increase, right? You can ask yourself these kind of questions. So you're kind of doing a self-validation of this problem. So this logistic regression, it scales between 0 and 1. So those are our two classes. 0 meaning that the patient did not die while they're in the hospital, and 1 means that they did. And logistic regression is not a very new model, right? This is not AI, right? This is not a very new thing. But surprisingly, even though this model is very simple, it's actually very powerful and surprisingly accurate for many applications. On the right here, I tried out another model that's called a random forest. A random forest is a really complicated way of saying there's a bunch of decision trees, okay? Each of these trees right here is just a decision tree where you're taking all of your data and you're splitting your data based off of some conditions. So for instance, you might ask whether you're going to ride your bike today, okay? And you might have 40 days of examples, right? And then for the first split might be, oh, did it rain today? Okay, and it turns out that it rained during 10 of the days and you didn't bike on any of those days. Right, so we would, then the remaining examples is 30 on one side of that decision and 10 on the other side, right? So we would say that this split in the data has a high degree of purity, right? And the higher the purity of the splits, essentially those splits are higher up in the trees. But the problem with a decision tree is you could split the data all the way down to single examples. So each of the leaves on the bottom of the tree is each going to have like one example, right? So in principle, this model can actually overfit to your data set. And one way that you could deal with that is you could train each of these trees using a different subset of your data. And then the majority of the votes among all of the trees just determines which class that this model predicts. So that's why they call this an ensemble method, because you have many models working together to determine a class. And this is some kind of basic things, but I include it because I figure I have much more to explain to the beginners in data science and deep learning than to give somebody an understanding who's an expert in deep learning. So I just include these things. So there's each model can either be underfitted to the data set or overfitted to the data set, okay? What underfitting means is that your model doesn't have enough complexity to capture the true shape of the data set, you could say. In the top left here for regression, you could see that this data sort of has a quadratic shape to it, but you instead decided to fit just a line to it. So you could see that this model is not really an appropriate choice for this data set. There's a high amount of bias in this line, and it's underfitted. It's clearly underfitted to the data set, okay? On the other hand, to the right-hand side, you could see this squiggly line here. It means that you introduce too much complexity in the model, and you're fitting essentially the noise in the data. Inherently, for any data set, there's some noise, right? And you're actually using a function that's too complex to fit to this data set, okay? So you need to strike a balance between these two, because this model on the left, it's not going to be very accurate. So it's going to perform not quite as well as you want it to. But this model on the right, it may fit this data set really well, but as soon as you use this for machine learning, introducing new data to it, it's not going to perform the way that you want it to. So you have to kind of strike a balance here in the middle. And often at times, this comes to how many features do I choose to represent this problem, and which model am I using? So often at times, this is also why it's a good idea to choose a simple model if you can. Okay, I chose the 200 most significant features in this data set based upon their representation among all of the patients. And I sort of chose the most significant features and narrowed it down to 50 for each of the patients. So these first two columns here are logistic regression, which I just told you is a pretty simple example, a pretty simple model. And actually, just by reducing the number of features from 200 to 50, you can see the accuracy and the model actually went up. Well, why is this the case? Because the more features you're introducing to describe your problem, you're going to be able to train a more accurate model, right? It's going to be more accurate on the data that you use to train it. But when it actually comes time to testing the model, it's going to perform really poorly. So that's what I show here, the accuracy. Logistic regression actually performed really well for this application. And random forest and neural networks performed really well as well. And in particular, these models perform really well when there's a strong amount of relationships between your features. So not just every feature is independent of each other, but two features have a strong relationship with each other. So you might choose those models in those kind of cases, but for this application, I chose to use logistic regression as my best model because it's interpretable. And in this case, physicians, doctors, they want a model that's very interpretable. For my neural network, I used a deep neural network. And indeed, it did give me higher accuracy. But again, for this application, it's important to be able to justify why are the predictions of the model being made to the doctor. And that's what they want to know. They want to have some confidence in this application. Maybe that lime thing that you were showing would work really well here. So what does this look like? It has pretty high accuracy and sensitivity. So sensitivity is the opposite of the false negative rate, like I was saying before. And specificity, this is the true negative rate. So what are some other practical considerations? We should always use two data sets in this kind of problem. We use one data set to train the model, and the other data set we use to evaluate the true performance of the model. Because if you just use all of your data to train the model, you might be overfitting your data set. Okay? And you want to be able to use the other data set to evaluate how is this model going to generalize to actual data in the real world. Another question you have to ask yourself is it important to be able to deliver predictions quickly for your application? If you only have 1 second, say if you're Visa or something, you have to determine whether a credit card is a fraudulent transaction every single time, right? You might not have a lot of time to make that prediction because after the customer swipes their card, you know, they're waiting every second, right? So some computationally complex models that are potentially more accurate can be much slower, especially neural networks. So in practice, you want to make these neural networks as simple as you possibly can. Does your model generalize really well after seeing new data? After training a model, it might not have the same level of accuracy when you apply it to the real data. Okay? Also, will the features of your model be very difficult to obtain in reality? So you need to keep in mind also the features of your model that you're using. Are these features that can actually be obtained for the project that you're working on? So some future opportunities in healthcare, I think, are using wearable devices to monitor as well as to prevent health problems. I know for my very old mother, I would like to have something like this. Improving the accuracy of diagnostics for certain diseases, as well as turning general patient care into personalized treatments. I think this is an area of high impact. High throughput computational screening of potential medicines, so discovering new medicines as well as optimizing clinic performance by resource management. That's kind of the vein that this project goes in, as well as AI-based triage of patients in order to reduce costs. A little bit about me. I'm a PhD from UC Davis. I'm currently working at Carbon, which is a 3D printer manufacturer, and we are now hiring a couple of people. So if you know Tableau, you can email this guy, Rob Ray, down here. We're looking for a senior manager of marketing data science as well as software engineers. Thank you very much.
Hello everyone. Thank you again for joining us today. I am Khyati, and I would also like to describe about the project I did at Insight. It's called Deep Photoshop. So the name is kind of indicative of what it does. It's a deep learning powered Photoshop. And I would like to describe one use case that I thought about doing. It's like logo replacement. So this Deep Photoshop is basically a smart logo replacement tool, and the technique I have used is called image infilling. And so I'll just let's just dive in. So I am pretty sure everyone would agree with the fact that we see ads all around us, right? Like on the billboards, on public transport vehicles. So how many of you think that it's always helpful? Are they annoying sometimes? Who loves the ads on YouTube? No. So they are not always pleasant. Yeah, they definitely give information, but sometimes, like as you see in the picture here, there is this beautiful view of the mountains and there is a Coca-Cola banner right in the center. It definitely spoils the view, but also there is another issue here. If you try to share this thing on on social media, or in case you try to monetize from it, then you might fall into trouble, because Coca-Cola can claim copyrights on this image. So so that becomes like they can fine you. So why do you want to get into all those troubles? So that's why I took this project where where my focus is removing these kind of logos and ads from the picture. So a naive solution can be that we can just crop that part of the image, right? That's basically very simple. Why do you want to go for a deep learning approach? And we can also, and you must have seen some shows where they kind of blur some part of the image, like while they are talking about some product, because they have limitations. They do not want to advertise that product, or they cannot reveal the company, right? So they kind of blur it out. And it doesn't look visually appealing. So is there a better way to do this? Yes. We can replace that part of the image itself, and we can fill it with whatever the context of the image is, right? So as you must have already, known already that deep learning is very good at images, right? So then deep learning can help us here. So here is a picture. On the left, there is a person who is trying to do rock climbing, and there are a lot of white patches in the image, right? So it's an incomplete image, but we can use deep learning to fill those parts. And it kind of looks really like it is much better than what you would do if the image is everything is just spread out. Then you can't crop it, or you can't do anything with it. So this is actually a very good way to solve that problem. So this technique is called image infilling, where you are trying to fill in the gaps in an image, and that's what my project is focused on. So what did I do and how did I do it? So first of all, you have an image here which has a company logo. For example, here this is an image of a Google building. So it has the Google thing written on that building. And our target is we want to remove the Google. We want the image, but we just don't want that part. So it is done in 2 steps. So I have 2 models in the whole pipeline. So the first task is to identify the logo. So that is the object detection and removal part. It is a YOLO model. I'll talk about it in detail in the next slide. So after we recognize that this is Google, we would like to mask it out. So we have now an image with a white patch on it. So it's again an incomplete image. And now we can go ahead and try to fill the gap in the image. So that requires another model, which is the image infilling model. And this is a CNN, like convolutional neural network model. And finally, at the end, we do get an image which is the same but without the logo. So this is what my project pipeline looks like. Now we can go into the details of each model here. So the model so both of these are deep learning models. The first one is logo detection part. It's a library called YOLO, you only look once. It's designed for speed, and it's designed for a real-time object detection. So that's why I chose that, because I had always, as Michelle and Josh already mentioned, that we have a strict timeline to do the whole project. So I had initially thought about using it for videos, like they could scale it up to videos. But given the time constraints, I could not get there. but I had chosen this model because of the speed and accuracy that it gives. So currently the model that I have has this average IOU, that means intersection over union ratio. So if there is an image and your model predicts a box, so that is the predicted label, the predicted output. And there is also a ground truth that, okay, this is the actual place where the logo is. So there has to be some intersection in between that, right? The model output and the actual situation of the logo. So that is what is called intersection over union ratio, and higher the better is, the model is good if it's higher. So currently that I got 50%. And the second part is the infilling model. So this is the model which took the most time, and it is a convolutional neural network model. So CNNs, if you are aware of it, they are very good in image manipulation and object recognition. So it was a no-brainer that CNN should be the first choice for this project. I also thought of using the generative models, because I thought that it is a missing part and I could generate that. But CNNs are a lot less complicated, easy to train, so CNNs seem to be a better way to go forward. So one thing that one thing that I would like to point here is that we don't have ground truth over here. So imagine that you want to remove the logo. So you need training data set which should have logo and should not have logo, right? Because your output is the object without logo. So it's kind of contradictory. Like we cannot have a data set with logo and without logo. So how do you solve the problem then? You need some training data, you need the output also. How will you train the model? So I decided that we can design the infilling model so that it can handle any random image in any given way. So it is a general model, and then so we can train it in that way so that it's robust enough to act on any data set and any image. So basically I still had to use different data sets for training and testing, because for testing I'll give an image with a logo, but I cannot use that image for training. So basically I ended up using more than one data sets. So here are the data sets that I used. It was difficult to get exactly the pictures that I wanted, so I ended up scraping some images. So I scraped some images of buildings, because you will see a lot of buildings have like ads on them. So it was an easy way to get a lot of images there. And also some pictures, I found a data set where people are playing sports, because they have a lot of ads over there also on their shirts and all around the field and all that. So those two data sets were used for the image infilling model training, and the other logo detection model, I have used the Flickr 47 data set. So that has images of company logos of 47 different companies. Time to see some results. So the left side you see the image of Google, and the middle part is the masked image, which is the intermediate step, and the image on the right is the predicted image by the model after we get the infilling done. So if you observe the image closely for the second example, the second image of Google, which is on the bottom, on the rightmost side, if you see that the model has predicted the shadow of the building also. So it's tough to capture that context of the image, but this technique is a bit it is powerful, so that it could capture a good context of the image. It could predict that, okay, there is a shadow, and it could fill in that gap accordingly. Some more results here. Here again, the first one is pretty, it does infilling really well. And the second one, it's actually a different logo, like it's not the normal Google logo. Plus, the image is not in a very good condition. If you see that it's a bit dark image, it's not very well lit, right? But still we could get the infilling part almost like gone, right? We could infill the image really nicely. So that shows that with training, you can definitely get better results. And this was in the 4-week timeline, so I could not spend so much time in training also, but with more training, the results can be better than this also. So what were some of the challenges that I faced? Well, there were a couple, but I would like to focus on a few here. So first of all, generalization of the infilling model. Now, what does that mean? It means that you give any image, any random image of, say, an animal or a human being or a building. Your infilling model should be robust enough to fill that gap, right? So that can be done. It has been done, but it requires a huge data. Say we have ImageNet data set and say we have unlimited resources and a lot of time. So then we can go ahead and keep training the model for a month, and then we can get great results. But I just took the first step that I need to get something working, like building the skateboard and then again reiterating over that. So I kept on increasing the number of epochs, and this is where I could get, like after a week's training, I could get good results. Like even a day's training could give me some results, but they were really bad. But after training of like a week or 10 days, you could get reasonably good results. So in data, so deep learning is kind of computer intensive, but you can go step by step to at least know if you're going in the correct direction, and then go ahead and increase the data, increase the time that you train the model for, and you can definitely get better results. The other thing that you can observe here is the logo detection part. So if you see the image of the sneakers here, so it has the logo which is split. It's not very evident. So these kind of corner cases, it's difficult to handle such cases in the logo detection part also. So we need to consider all those aspects also for the whenever we are doing certain deep learning projects. The future directions that I could see with this project is we can definitely improve we can improve the images of the quality of the images that are being generated. So if you see the rightmost image of the building in the infilled part, you can see that there is some little blur, right? You can feel that it's not perfect, but you can definitely improve that if you put in more time for training. So, and as I said, it would be really exciting to see this go to scale to videos, because that's where I started from, like seeing the images which are blurred in the video in real time and being able to just remove that part. It is actually just a chain of images, so it is definitely possible, and that is the best part of this project. So this the other thing with my project currently is it's not able to handle any arbitrary shape image. It has to be in certain dimensions only. Like for example, the architecture of the project is such that it just accepts 512 cross 512 images, and this happens with a lot of deep learning projects also. We need to, so the data preparation part in any deep learning project, we need to make sure that everything is of the same dimension, and that's what we need to, that's a data preparation part of any deep learning project. So, so the cool part would be if we could make that also flexible, because so in infilling, I could actually, so you can see that the mask is pretty random. There is randomly shaped lines and circles, but it still does a good job. So the infilling part is taken care of. It's pretty robust to handle any arbitrary shape, but that's not true with the size of the image. So that is one of the things that could be improved here. So after doing all this, a question would be, is this really helpful? Do people use this? So I would like to point to an article which I used as a reference. This is the paper by NVIDIA Research. So they have done this infilling technique. They have proposed the changes in the infilling technique to do real-time infilling, and it's pretty fast and it's pretty cool. And I have posted the link for the YouTube also. And also there is a project from Adobe Cloak. So Adobe has the Photoshop, and this is a perfect application for that. So basically they also released this in late 2017. So yeah, definitely it has been helpful, and there are a lot of people in industry who are doing this. So I would go towards a conclusion that by saying that this was just an example of one of the use cases of infilling technique, but this technique is pretty powerful. It is basically a reusable pipeline. You can, if you have some other use case, this is just like removing logos, but you can think of a lot of use cases. One that comes to my mind is child censoring. If there is some images or some videos where you want to filter out content, you just need to do one thing. You need to train a model which can identify whatever you want it to. And then you can use this pipeline to feed in that infilling, logo detection model, and then you can infill the gap using the infilling model. So it's very reusable pipeline. Okay, so thank you again for paying attention. I am Khyati, and this is some of my work and some of the things that I do outside work. I like to go for outdoor activities, and currently I'm working at Cequence. Thank you.
Let's say if I Google anything, any addresses, in the road, there's a car on the road, they say number plate, they are using the infilling technique?
They are not, they are using, yeah, okay. Yeah, so there is a question. So if you see you have seen some object detection models, and you might see some cars going by, and there is a box over the license plate, right? So you're saying that does it use image infilling?
Yes.
It uses the YOLO.
Google never show that, like if you search any
Correct.
car, they Google the wiping out the numbers.
Okay.
Yeah, so are they using the infilling technique?
They are not using, they might not be using infilling, they'll just remove, okay, so they remove it and replace it?
Yeah, so if you see any cars on the Google map,
Oh, yeah.
so they cannot do it
Correct.
manually, right? They
Yeah.
must be using some model.
Yeah, so for that, so actually this infilling technique is pretty recent, but what they have been using is, so there are other techniques where you can just calculate the pixel combinations of the image and just remove that part. So that also is one of the techniques, but Google, for that license plate thing, I don't think they are using infilling technique.
Well, this is great. Just real quick,
Would you like me to help you with that?
Can I just escape this?
You might want to do this, this is to make
So, okay, the last
people
three
know you
digits.
hear you better.
Yeah.
So if you don't mind, I want to take this
Oh,
microphone
yeah, sure.
from you and put it on the table so that everybody can, oops, sorry. Thank you. Everybody can hear.
Oh, we have a winner. Thank you, O'Reilly, one more time. Do you have something else?
912. 912. Anybody?
I don't think that's working. Is it?
Yeah, we're going to pass on.
What are you doing next?
I don't think this works.
903.
Now it should.
Okay, I should use this mic.
No, this is for streaming, for all of you to share. So this will be listening to all of you, and you will be using this.
I'm not streaming, but I'll just lean over.
Oh, well, you can use
Let's
this.
go ahead and turn
This
it over to the
microphone.
panel now.
Okay.
And this microphone will capture all of you.
Okay. Okay, so thank you again for everyone for staying this long, and again, I appreciate all three of you for taking your time out from the evening and sharing about your projects here. So let me just start off with a couple of quick questions, and then we open up to the audience. Michelle, you gave us a little insight into the Insight Fellowship. So what I would like to hear each of you kind of give a quick brief summary of where were you in your career journey, why did you choose Insight, and how it has helped you. So for other folks here, they may think about it as well.
Do you want to start? Sure.
Okay.
Yeah, so I was in my last semester of my master's where I came across this Insight Fellowship, and I came to know through our school itself, and I had a couple of seniors who also had taken this fellowship, and they highly recommended because they really had a very good experience, because Insight basically gave me a broad overview of all the cool things that are going on in machine learning, and a very good platform to explore these opportunities. So like doing a project in 4 weeks, I would have never done that if I was not a part of Insight. And it is the techniques the things that we learned from our experiences that, building out really fast and iterating over it, and then, so those are the industry level those are the things that are really valuable at an industry, regardless of which domain you are. And I got to learn all these things through that program itself. And also towards the end, we get to interact with a lot of companies, so we get to know really like what exactly our role would be, and a lot of insider view kind of thing before we even joined. So that gave me a lot of clarification of what I want to do and why I want to do it. So that was really good.
Good answer. Thank you. So I'd say my perspective on Insight is I did it to expand my perspective and also to build a lifelong network. So a great example is when we were putting together this program tonight, I was originally slated to speak, and I said, let's add some more folks, and within a very short period of time, we had both of them lined up with, as you saw, some great things to talk about. So it's certainly that. And then the other thing I found was that, an opportunity to work with folks like Josh and Khyati and our cohort of about 30 people in the AI engineering program, that for me was, many of those brought a different perspective than I did. So my background is in production level, scaling, global data, from both a software engineering and data science standpoint, and most of the cohort is from an academic, in our cohort was from an academic background, Josh included, and it was very interesting to me to get in and talk about projects and problems where when they said 4 weeks is our project, these folks had spent 4 years or more doing their PhD, and my perspective was, 4 weeks, that's 2 sprints, right? I have 2 sprints to do this. And then, talking about, well, here's your model, and, when you put that into production, how might it perform? Or, is that question off the table? Do we not put it into production? Do we just want it to get, to a certain success metric? So I really did appreciate that different perspective.
So there was primarily 2 different types of people that are inside, or if you could say that, like at high school you'd be like the jock or the nerd or whatever, but at Insight you had people whose background, I don't know, but you had people whose background primarily was like a software engineer, or like somebody from graduate school, like a PhD scientist kind of person. So what Michelle says is true. But for me, on the other side, I have a PhD in chemistry, and I was very intimidated by all of the software engineer people that were coming into the program. So it's very interesting. I think currently some numbers about Insight is I've heard that for the data science program, it only has about a 7% acceptance rate. And for AI, it's a newer program. It hasn't fully matured yet, but I think in that one, about maybe a 20% acceptance rate. And I think for me, as a computational chemist, I was doing machine learning like my entire graduate school. I just didn't know that it was called that. And I think that there are many people out there that are really, really trying to get into this hot new field, but there is not enough supply in terms of educational resources to do that. So for me, Insight really helped me to put something on my resume that people would take me seriously. They would take my job application seriously. Yeah, but I heard about it through my wife, who is also studying to be a data scientist. And I hope I haven't wandered too far off from the original question, sorry.
No worries, thank you for sharing. I'm sure the audience has additional questions. Just another quick follow-up. In your projects, and we heard today 3 different areas where you had applied your AI engineering skills. What were some of the aha moments maybe which you didn't know coming in while solving? And it could be on the data, it could be on the model. I think you touched a little bit, maybe if you could just quickly summarize.
Yeah, so basically we had a week to decide and brainstorm about the idea that we were supposed to work on for the next 3 weeks. And what I would say, I felt that I had to choose something which I could basically implement in 3 weeks, like from scratch to presentable situation. And I also had my master's course with this fellowship, so I knew my limitations and I did not want to choose a very complicated problem and just end up doing nothing. So, but that actually happened. I still failed to validate the whole flow before in that 1 week duration, and I had to struggle a bit for I was lagging behind in my project for a while, but that was an experience, a learning experience that you really need to think about the whole thing, have like a first check that you will be able to do this for the next 3 weeks within the 3 weeks period. Yeah, so, but it was a good learning experience.
Yep. So before I tell my takeaway, I'll say the rest of the program, so it's actually a 2-month fellowship, so what do we do the rest of the time? We do training, we do drills, we do whiteboarding, we do theory. Everyone needs to present on something they're expert at and teach the rest of the group. So it's quite collaborative, a lot of whiteboarding, a lot of drilling and things like that. So it is a 2-month program. And I'd say my aha when I was doing this is really 2 things. One is I love the approach of, stick in your mind the bulldog on the skateboard, right? Get your skateboard going. And I think when, speaking for myself, when I came in, it was, I want to do this really, awesome project and doing something, really step it up and doing something complex. And they really coach you to, get a skateboard going, get a simple model going, start with the simplest model possible, and everyone was sort of like, oh, logistic regression, are you kidding me, right? But, just get something running end to end, right? Because you'll always, chances are you'll learn something very material that causes you to course correct or, whatever, versus if you had just jumped into deep learning. So the first is, always get a skateboard going, get the simplest model going possible. And my second aha with deep learning, after I did that skateboard and adding deep learning is, deep learning is so achievable, it's so doable, and it's so learnable. And as I said, the project I showed you for crypto predictions is, the deep learning part is about a page of code, right? So, and I also showed you a deep learning example with 7 lines of code. And so, it took some of the mystery out of it for me. It showed that it can be done, started, MVP'd in a discrete amount of time, and some very, very doable ways to get there.
Can you hear me? Oh yeah. Yeah, I would say it's hard to pin down to just one aha moment. I think for me it was just discovering there were so many other people that were really excited about the kinds of projects, and also just the similarity of different projects. Like in one case, you could have a model that detects cats in images, and then over here, you can use that same model to detect cancer in somebody's lungs. You know, like that's just so the surprising level of transferability of like different models and different ideas was the aha moment, I guess.
Thank you. We are at 8:33, so I'm just going to open it up for questions from the audience. Do we have enough mics? Or?
I'm just curious, in your opinion, where is the action today in deep learning? Is it large companies? Is it small companies? Is it academia? Is it all over? Is it who's really kind of driving new stuff, models, new approaches?
The action is right here. Do you feel like you can speak to academia?
Yeah, I know from experience, and I haven't done deep learning in academia, but after interacting with other academics, there are certainly people that are trying novel architectures in deep learning, as well as trying to improve the practicality of deep learning, because we call it deep learning, but actually, in order to train a neural network, you need to show 1 million images of a cat in order for a network to recognize a cat. But to a little kid, you don't need to show them 1 million images of a cat, do you? So a lot of the improvements that I'm seeing are about improving the common sense of neural networks and deep learning in order to improve their function and their practicality for real world situations.
Right, and to add to that, I heard a great example, which is a data point of 1 for real world understanding, which is if you're even a baby and your hand touches fire, you pull it back and you don't touch fire again. You have learned that you don't touch fire, and it's conclusive and it's correct, right? Deep learning in industry, I would say, you know, there's so much potential, it's just starting. I shared that stat, less than 1% is using it in production. We saw that it was a little bit more here in this crowd, but not too much more. So in my mind, that's a big opportunity. I have heard feedback that because the results are not interpretable or as interpretable with deep learning, as easy to explain and understand what the models are doing, people in business use it less for that reason. So imagine you're coming to, you know, your board and explaining something, or your manager and, you know, trying to get funding, and they say, well, you know, show me why, and you say, well, the model told me so, right? If you understand what the model is doing, it makes a lot of sense, but if you're maybe more arm's length, it's less digestible. So I see some of that going on. Do you have any perspective on that?
I feel that it is becoming a buzzword. Like when I was in my master's, there was a deep learning course. That was the first time deep learning was offered in school. So it is kind of becoming, everyone wants to do deep learning, and I have seen, I would say it is all over, because I've seen startups coming up with really cool ideas to do that, like use deep learning in ways. Also bigger companies like car companies want to do self-driving cars using deep learning models. So it is kind of all over, but yeah, it has specific applications. Like it is not for all type of projects. In healthcare it might not make sense because it's not interpretable, but it is still finding a lot of applications in other areas. So that's what I would like to say.
I'm going to add one last thing, if it's fine. So I would say that a surprising amount of the deep learning community has gone open source. And so it's difficult to pinpoint any one group of people where the action is coming from, because I mean, Google is making TensorFlow, and this is openly available to everybody. And Keras and Yeah, there is surprisingly amount of open source material, so the action is at the boundaries between these different groups, I would say.
Thank you. I think we'll do maybe one more question because we have to clear the place. How much time do we have, Liana? Okay, I think we'll do one more and then we can stay. So we have one mic here.
Hi, so I have two main questions. My first one was regarding interpretability. So in both of your examples, Josh, I'm sorry, I can't remember your name, but in both of your examples, you were looking at data, and in that data, you were unable to kind of attribute which features were highly correlated with the problem that you're trying to predict. So, I mean, in economics, it's pretty clear that you can test for causality, but it seems like in machine learning, there isn't like a systematic approach as to see which feature should I drop, which one should I include, or if there's missing data, how do I handle that? So as a person that's kind of interested in going into this field, and how do you approach those problems? Is there like a common way that many data scientists might handle this issue?
Are you referring to my project or my project or hers?
I mean, just all three.
Yeah, that's a very, very difficult question. I think feature selection, I don't think the field has settled on any single way that is the best way to engineer or select, or in terms of feature selections or filling and missing data. I don't think anybody has really settled like on what is the best way to, that there is one method that is the best way to do that. Certainly, if it helps to improve the performance of your model, that's great. And often at times, in my opinion, I think the simplest models, if you could get a high degree of accuracy with them, I think that they're some of the best models because we understand them. And other people trust them more. And that's important in a business too, where especially where data science might be a new thing at your business. So
I would like to add to that. So basically, that's where human intelligence also comes into picture and domain expertise comes into picture. Like data scientist alone would know which models to use, but the person from the domain will be able to choose help in the feature engineering part because they have seen through experience. That's where, like Josh mentioned, that they will know what features out of the 200 will be more important. So in a way, it's not a solved problem, but like collaborative effort, and also it depends on problem to problem. It's very different for different problems. The level of this complexity of this issue. It's an important part. It's a major chunk of where our time goes.
Okay, thank you everyone for joining us. A big round of applause for